The question before us now is, given a multi-layer neural network, how do we train it? How do we learn these weights? Well, we got a little hint of this early on when we derived the delta rule that says for a single neuron and for a single weight associated with a single neuron, how do we learn it? And it was a version of iterative least squares or gradient descent. We've got some quadratic error function we established, we compute some derivatives, and we get the update rule on how to move through that quadratic space. And training this type of network is basically that, but on steroids because of the complexity of the interactions. And the core underlying methodology for training a modern neural network is backpropagation. I'm going to go ahead and warn you, we are not going to do this in detail, but I do want to give you an idea of how it works to give you some intuition. At the end of the day, when you go to implement one of these neural networks, you will not be implementing these optimizations yourself. These will be provided to you in whatever package you are using. But it is good to understand and to see how this is just a slightly more, and in some cases, a much more complex version of the simple delta rule that we use when we only have that single neuron and that very simple linear model without the hidden layers and without the multiple connections. So let's see what we're going to do here. So we're going to start again with a quadratic error function. That's not different. We have a label associated with this output right here. Let's call that z sub l. And we have the output that comes out of this. And we just want to minimize the sum of the squares of all those deviations. I've added a 1/2 here because when I go to compute the derivative, that 1/2 is going to drop off. It obviously makes no difference here since I'm trying to maximize or minimize something. So look, right out of the gate, there's something cool here. We're just minimizing a quadratic error, but it's just going to be a much, much more complicated quadratic error because of the underlying structure that you're seeing here. Okay, let me define a few things. Let's let arbitrarily, I didn't have to do this, but arbitrarily, let's let this output neuron have a sigmoidal nonlinearity associated with it. So out of this, the y hat, the kth neuron of the output, which is the superscript here, is equal to 1 over 1 plus e to the minus whatever comes out of the linear model in that neuron, which is just this right here. So this little guy is taking a bunch of weights associated with the inputs that come from, notice the h right there, from the hidden units, right? So we're going to talk about updating these weights first because they're a little bit easier, and then we'll talk about updating these weights here between the inputs and the hidden layers. All right, so what do we want to do? We want to take the derivative of this error function with respect to, let's just do this one weight right here. Remember that every one of those connections is a weight whose value needs to be learned. So let's just look at this one that connects the jth hidden neuron to the kth output neuron and ask, what is the update rule, the delta rule, associated with this? So we're going to play the same game. We're going to take all those weights there, we're going to randomize them, or maybe not randomize them, maybe start with a slightly better position, and then start to update them according to a rule that we're about to derive. And here's where things are going to get messy because of the interconnection here. This derivative is equal to, we have to apply the chain rule, and it's sort of the nightmare of all chain rules because we have to take the derivative of e with respect to the output, the derivative of the output with respect to the before the nonlinearity, and the derivative of that, what came out of that nonlinearity with respect to the weight. There's 3 parts to this. The weights come in, they get summed up, and they get multiplied and summed up, and then we put them through a nonlinearity, and so we have to do the chain rule through each of those steps. I'm not going to take you through all of this because frankly it's a little tedious and you don't really learn very much, but these 3 partial derivatives here are enumerated right here. And they're actually not that bad. They're related to the label, z sub k, relative to the output. And then the output of the nonlinearity, and then the output of the hidden layer. So I've got 3 partial derivatives here, which if you're inclined to, you can actually compute by just computing the derivatives of these 3 here. And we now multiply all those together, and we get this little guy right here. And this is the delta rule. This is it. Once you compute the derivative, that tells you how do I move in the negative direction. There's the negative sign right there. Why? The gradient tells you the direction of maximal change. You want to go down because we're minimizing. So now I've got the product of this term, and this term which is right here. And then I've got this alpha here, which is my step size. So for the j-kth weight between a hidden layer J and an output layer K, here's my update rule on how to move from the current weight to a better solution. Not that bad, it's just a bunch of calculations, but of course all that is just for one weight. Now I could have done that for every single one of these links between a jth hidden and a kth output, which I will have to do for a fully connected network. Now where things start to get messy, if that wasn't messy enough, is having to figure out these weights. And the reason intuitively is this. This weight here is connected from the input, the ith input, to the jth hidden layer. But it ripples through to all of the outputs. And that means that a change that I make here, I need to understand the impact on not just one output, but on all of the outputs. All right, we're going to play the same game. We've got an error function. It's quadratic. I'm trying to minimize the sum of the actual labels and the outputted labels squared. I'm going to have the same nonlinearity for the hidden unit. That's just one that I've chosen. It's just the sigmoid. And that's the output. That's the linear model here. That's the nonlinearity here. Same game. Take the derivative of this with respect to the ijth weight between the input and the hidden unit. Apply the chain rule. And here, I'm really not going to go through this because this even gets worse, because this derivative right here, just this one, you have to apply a whole nother set of chain rule because of this ripple effect. And there are many, many good online resources if you are inclined to go through all these derivatives, but it is a little excruciating. Here are the rest of the partial derivatives. I multiply them all together. I've got the negative because I'm moving in the opposite direction. There is my weight alpha. And now I have my update rule for each connection between an input and an output. I recognize I didn't do that in enough detail for you to implement, although you will never have to implement this because this is built into the library. What I wanted you to see that at its core, what we are doing is not that different than what we did for a single neuron. We took an objective function, a quadratic error function. We want to minimize the difference between the actual labels in the label training set and the predicted labels. And then we say, all right, that's a quadratic error function. I'm starting at some point in my weight space, and I want to move towards the minimum. Compute derivatives, and then move in that direction. And the only difference with these fully connected multi-layer networks is that those derivatives are a little complicated because of the interconnection and the resulting chain rule that you have to apply to compute the derivatives. But once you work through it, you have an update rule for all of the various weights. Okay? And it would seem like, okay, that's not a big deal. Maybe I didn't understand all the derivatives, but how hard can this be? Where this gets tricky and where the black art of neural networks comes in is that the computational efficiency of simply blindly applying the backpropagation doesn't really work in many, many cases because the networks are huge and the training sets are huge. And so a lot of the black magic is in things like stochastic gradient descent, where you sample the data differently in order to be computationally more efficient. How do you determine the step size? Should the step size be the same? Maybe it should be bigger in the beginning and smaller at the end when you're refining. And there are all these tricks of the trade that emerge and all these hacks that emerge and some black magic, frankly, that emerges in order to get that optimization to work efficiently and to converge at something that is going to give you good classification. But behind the scenes is frankly nothing more complicated than the delta rule on steroids because of the interconnection of the networks. And again, those networks with hidden layers and nonlinearities can in fact do remarkable calculations, but getting the network to train and to converge and to find that is a huge challenge. And that, of course, is the challenge that is facing neural net approaches to the types of machine classification problems.